Hi, this is Sir Aris. Today let us talk about Chapter 2 on complex numbers. We'll first discuss on short introduction, real and imaginary parts of a complex number, the complex plane, terminology and notation, and some complex algebra. As an introduction, remember that the general solution of the quadratic equation given by this expression is for z unknown given by the quadratic formula, this expression. This term inside the square root, we denote that as d equals b squared minus 4ac is called the discriminant. And the solutions of the quadratic formula are two distinct real numbers if and only if the determinant is greater than 0. They are repeated real numbers if and only if d is equal to 0, and complex if and only if d is less than 0. We use the symbol I uh, if we have the third uh, classification here, where the discriminant is less than 0 or uh, containing a factor of minus 1. So I squared is equal to minus 1. For example, we find the solution of z squared minus 2z plus 2 equals 0. So using the quadratic formula, we can simply write z as negative of minus 2 plus and minus square root of um, minus 2 squared minus 4 times the coefficient of z squared, which is 1, and this term, which is 2, divided by 2 and this coefficient 1. Okay, so you have minus and minus, so plus and minus square root of 4 minus 8 all over 2. Okay, so we get here 2 plus and minus negative 4 over 2, or this is 2 plus and minus 2 square root of minus 1 over 2, or this is simply 1 plus and minus square root of minus 1, or 1 plus and minus I. Um, so this is the solution for z. In a complex number, there's a real and imaginary parts. For example, if you have this complex number is 7 plus 4i, 7 is the real part, 4 is the imaginary part. Take note that we label 4 as the imaginary part, not 4i. Now, if the real part is 0, the complex number is called imaginary or pure imaginary. For example, if you have 0 plus 3i, the real part is 0, and this can be written simply as 3i. If the imaginary part is 0, so we can write, for example, 8 plus 0i, we can simply write it as 8, and it is uh, a real number. Now we can also write the complex number 7 plus 4i as an ordered pair. 7, 4, we write the real part first and the imaginary part next. In a complex plane, the ordered pair 7, 4 can be plotted as the coordinates xy on an xy plane. So if this is an xy plane, so we mark the coordinates. So let's say this is 2, 4, 6, 8, this is 7. Okay, so this line here are points x equals 7, and then suppose it's 2 and 4 on the y-axis. So these are points y equals 4. So this intersection here is our 7, 4. And this is the point 7, 4 on the xy plane. Now 7, 4 can be written as 7 plus 4i, a complex number. So we can plot x plus iy on an xy plane. So if you have a complex number given by x uh, plus iy, we can create axis x and y, so that, for example, this is an arbitrary x and arbitrary y. The intersection is called your point xy. This plane is called the complex plane, or sometimes called an argon diagram. In this complex plane, the x-axis is called the real axis and the y-axis is called the imaginary axis. So complex numbers written in x plus iy form are said to be in rectangular form. We typically call the xy coordinates as rectangular coordinates. So we plot xy in the complex plane. We can also use polar coordinates r and theta, with r the distance from the origin to the point P. So if we make a plot of our x and y coordinate system, or an x and y complex plane, suppose these are x and the arbitrary value y, let's call this our pxy, and this distance is r. The angle measured counterclockwise from the x-axis to the line connecting the origin, so this is the origin, and p, that's theta. We can also write the complex number in polar form. Before that, let's take note that here from this diagram, x is written as r cosine theta and y is r sine of theta. So this is our y. We simply use um, the trigonometric identities. So if you have x plus iy, that is r cosine theta plus I r sine theta, or r cosine theta plus I sine of theta. This term here, we can write it as exponential of I theta, where, so this is our uh, polar form, where E I theta equals cosine theta plus I sine theta. This is called the Euler identity. For example, let us write 1 plus I squared of 3 in polar form. So 1 plus I squared of 3, if we compare that with our x, so this is our x and this is our y, it tells us that um, the value of r, which I forgot to mention here, r is the distance from the origin to the point xy. So simply r is equal to square root of x squared plus y squared. Okay, so here we can easily find that r equals 1 plus, or 1 squared, square root of 3 squared, and that would be 1 plus 3 or square root of 4 or 2. Okay, now we want to get theta also. How do we get theta? Here, this theta is related to x and y by the expression tangent theta equals y over x. So our tangent theta, which is y over x, y is square root of 3, and x is 1. So this is equivalent to, remember, tangent theta equals square root of 3 tells us that um, theta is equal to pi over 3. Okay, so r, or x plus iy, so let me write instead of x plus iy, 1 plus I squared root of 3. 1 plus I square root of 3 is equal to re theta. R is 2, e to the I theta, I mean, pi over 3. Okay, now let's proceed to the next section. Um, we typically call a complex number z, and this is equal to x plus, this is supposed to be plus iy equals r cosine theta plus I sine theta, or r times e to the power of I theta. Z is our complex number, x is the real part, or we call the real part re of z, and the imaginary part of z, which is y, I am z. R is called the modulus, or the absolute value of z, that's given by, denoted by mod z, or x squared plus y squared. And theta is the angle of z. It's also called the phase argument or the amplitude. Now let's write z equals minus 1 minus I in polar form. Before writing it in polar form, you can look at the plot. So suppose this is our x and y axis. This is minus 1, this is 1, 1, minus 1. So minus 1 minus I has a real part minus 1, so over here, and imaginary part minus I. Okay, so it will only be this point here. Okay, to go from x-axis to here, we go, this is 90 degrees, 180 degrees plus 45 degrees. So this 45 degrees is pi over 4. Now we go 5 times, so pi over 4 plus pi over 4 plus pi over 4 plus 5 over 4, pi over 4 plus pi over 4. That's the theta would be 5 pi over 4. Now that's not the only value of theta. If we go around one full revolution, we go back to the same point. Or we go back to this point here. So technically, theta could be 5 pi over 4 plus an integer multiple of 2 pi. So let's call that 2 and pi. But it would be enough to use n equals 0 or theta equals 5 pi over 4. And if we do that, um, our modulus of z, or z absolute value, that's simply 1 plus or negative 1 squared plus negative 1 squared. Take the square root, that would be square root of 2. Or finally, we have z equals square root of 2 e to the power of I 5 pi over 4. Okay. We can also write complex conjugates. So the complex conjugate of x plus iy is obtained by changing the sign of I. So we get x minus iy. We by the symbol would be z star, z asterisk, or z bar. So if you have z equals x plus iy, z asterisk is x minus iy. In polar form, if we have um, x or z equals x plus iy, z uh, modulus, or here we can write this as r cosine theta plus I sine theta. So this is r cosine theta minus I sine theta. Okay. Um, hold on. This is let me write this again. This is r cosine theta plus I sine theta. Z bar or z asterisk would be r cosine theta minus I sine theta, or r e to the power of minus I theta. Okay, now let's do some algebra consisting of complex numbers. Um, First, let's try to write 1 plus I in x plus iy. So to do that, we simply expand this 1 plus I squared. So that's 1 plus I times 1 plus I. That's 1 plus 2I plus I squared. Or 1 plus 2I minus 1. This one is minus 1. So we are left with simply 2I, or 1 plus I squared equals 2I. Okay. Now how about a fraction? 2 plus I divided by 3 minus I. We write it in x plus y iy form. The technique is to eliminate this complex number in the denominator by multiplying with its conjugate. So we have 3 plus I, 3 plus I. So if you do that, you have here we multiply the numerator, 6 plus 3I plus 2I plus I squared divided by 3 squared minus I squared, or you have 6 plus 5I minus 1 divided by 9 minus negative 1, or that's 5 plus 5I divided by 10, or 1 plus I all divided by 2. Okay. Another example, we want to write 1 plus I squared in polar form. We already have this answer here, so that would be that could be easily written in polar form. We have 1 plus I squared is equal to 2I. So here y, this is our y, so that r is equal to x squared plus y squared. That's simply 2. And tangent theta equals 2 divided by 0, so that would be infinity, and the smallest number is pi over 2. Okay, so this we can write as um, 2e to the power of I pi over 2. Alternatively, we can write we can write in complex or in polar form 1 plus I. So with 1 plus I, r would be, so in this case, here r is 1 plus 1, the square root of 2, and theta would be pi over 4. Okay, pi over 4, that's tangent theta is 1 over 1, so we have 45 degrees, or pi over 4. So this would be square root of 2e to the power of I pi over 4, so that 1 plus I squared is the square of this, that's 2e I pi over 2. Okay, now let's write um, the complex conjugate of z1 plus z2. So z1 plus z2 in complex conjugate form, that would be x1 plus iy1 plus x2 plus iy2, all taking the complex conjugate. So that's x1 bar minus iy1 bar plus x2 bar minus iy2 bar. Or this is simply z1 bar plus z2 bar. Or we can also write this as x1 plus x2 minus I y1 plus y2. Okay. Now let's try to find the absolute value of z. So if we have z absolute value, we know this as x squared plus y squared, then you take the square root. Take note that this is equivalent to x plus iy times x minus iy, which means that we can write the absolute value of z as z times z star, and then you take the square root. Okay, an example. Find the absolute value of square root of 5 plus 3i divided by 1 minus I. There's a hint the absolute value of quotient of two complex numbers is the quotient of the absolute values. So here are square root of 5 plus 3i divided by 1 minus I. That's equal to square root of 5 plus 3i divided by 1 minus I. Okay, now taking square root of 5 plus 3i times square root of 5 minus 3i divided by 1 minus I times 1 plus I. And that's simply 5 plus 9. Here we're supposed to take the absolute, or the square root. Okay, so square root of 5 plus 9 divided by um, square root of 1 plus 1, or that's square root of 14 divided by square root of 2, or that's square root of 7. Um, let's find an equation. Let's solve an equation of complex expressions. So um, an expression where the real and imaginary parts are variables x or y. So generally, two complex numbers are equal if and only if their real parts are equal and their imaginary parts are also equal. So what we mean by that is, here, if you have this problem, um, what we do, we can expand this term. So it's x squared plus 2ixy plus y squared, or that's y squared, which is minus y squared equals 2i. Or rewriting, we get x squared minus y squared plus 2ixy equals 2i. Now if you compare the left side and the right side, this x squared minus y squared, which is a real part, has no counterpart here. So basically we can say this is plus 0 real part. So x squared, this means that x squared minus y squared is equal to 0. Another equation is that this should be equal to this, or that xy equals 1. Okay, now if you use this first equation, you get x equals plus and minus y. And then if you substitute this to xy, you get, so here, um, substitute to xy equals 1, you get um, plus and minus x squared equals 1. Now since x is real, then x squared should be greater than 1. So x squared is equal to, this is greater than, not 1, but 0. Okay, so x squared should be equal to 1, which means that x is equal to plus and minus 1, telling us that um, not only is x equals, or plus minus 1 is x, that is also our value of y. Okay, now let's look at graphs of some complex numbers. If you have z equals 3, this means that x squared plus y squared equals, take the square root, that's equal to 3. Or x squared plus y squared um, equals 3 squared. Okay, this plot is a circle of radius 3. How about this one? This is x, or x squared x plus iy minus 1 equals 2, which gives us x minus 1 squared plus y squared equals 2 squared. Or a circle of radius 2, center at 1, 0. And this one here is the region inside, um, or the region inside the circle B, including the um, circle, or including the border. For this angle of z equal to pi over 4, um, if we get tangent of theta, tangent of pi over 4. Um, that's our y over x. This tangent is equal to 1, so that means that x is equal to y, or that's a line, okay, with slope 1. How about the real part of z? So for the real part of z greater than 1 half, it means that you have x plus iy with x always greater than 1 half. So if we create a plot xy, this is say 1 half, then that would be a plane greater than, so all of these points here would be our points with the real number z greater than 1 half. Now finally, let's consider a particle moving in the xy plane. Its position xy is a function of time t given by this expression. We want to find the magnitudes of its velocity and its acceleration as functions of t. Let's define the complex velocity and complex acceleration by this expression. Um, if you want to find, say, dz by dt, um, the absolute value would be, so v, or the magnitude is dz by dt, absolute value. That's dx by dt squared plus dy by dt squared, which is just the components, which are the components of this complex number, the real and imaginary components. So to get this, we can simply use this expression. Okay, so dz by dt is given by the derivative of I plus 2t divided by t minus I, which is simply t minus I squared, t minus I, um, derivative of this, which is just 2, with respect to time, minus I plus 2t, derivative of the denominator, that's 1. Okay, so we have here 2t minus 2I minus I minus 2t, t minus I squared, or 2t's cancel, so you have minus 3I divided by t minus I squared. And to get the absolute value, dc by dt, we get the absolute value of minus 3I and t minus I squared. For this 3I, the absolute value is simply 3, whereas here, the absolute value is, we can write it as t squared plus 1. Um, you take the square root, but then you're taking the square, so that would be 3 over t squared plus 1. That's our velocity. Okay, now for the acceleration, we need dz, d squared by dt squared. Before that, before taking the absolute value, let's solve that first. That would be the derivative of this. Okay, so we take the derivative of minus 3I t minus I squared. That would be minus 3I times minus 2 times 1 divided by t minus I to the power of 3. And that's 6I over t minus I to the power of 3. Or finally, we can have the absolute value as so the absolute value of 6I divided by t minus I times to the power of 3. Okay, or you can place the 3 inside first and then take the absolute value. In this case, it would be easy to get that 6 divided by t minus I, so that's t squared plus 1, take the square root, the power of 3. So this is equal to 6 divided by t squared plus 1 to the power of 3 halves, which is our acceleration.